This is actually the lab from Canvas. I recommend printing this out soon if you have not done so already. And the reason why I recommend printing it out is because it actually has a summary of last Thursday's lecture in here. So it goes over all the different what's causing the IR, little details. You have your little summary here, the chart. And then you also have, these are the crucial pieces of information. You have the correlation charts, which you are going to want. Okay, so just a little recap of last time. Let's take a look here. So infrared spectroscopy is one of the three main forms of spectroscopy that we use in organic chemistry. One of them we hadn't really mentioned yet. So the main three are infrared spectroscopy, that we use for looking at functional groups. The other one is Nmr Spectroscopy. That stands for Nuclear Magnetic Resonance Spectroscopy. We actually use that for looking at carbon backbone detail. A little aside of interesting about the NMR is when they first came out with NMR, it quickly led to the ability to make actual images with this technology. And we actually call that the NMRI. And it stands for Nuclear Magnetic Resonance Imaging. Because of this, the time it came out, people were worried about radiation and nuclear, so they dropped the N off, because this is actually working off of magnets, not off of nuclear radiation. And we now call this the MRI. So when you guys are you see at the hospital, the MRI, the fundamental basis of that technology is from NMR. So that led to MRI. But yeah, we'll get into all that magnet stuff and everything, but when you have the big thing spinning around you, I like to equate it if they're putting your whole body in an NMR tube and just throwing in an instrument. That's basically what they're doing. So they're putting your whole body in there versus a little molecule. The other form of spectroscopy that you guys have probably heard of is mass spectroscopy. It's actually very commonly used in organic chem, and we're just going to touch on the basic gist of what that is and some small calculations, and that's all during the last stuff. So once again, right now we're going to do IR. We are going to carry IR until the end of the year, and we're going to have it on every exam and labs here and there as we go along. At the end of this semester, we're going to introduce NMR and mass spec, and then from then on till the end of OChem 2, we'll be doing NMR and IR on every single test. So you guys are going to be pros at this stuff. All right. So going back to the IR thing here, here's a little illustration of what's happening. So basically, your light comes in, it can hit a bond and cause it to vibrate, and that is called absorption. And we can measure these absorptions. It turns out that every possible variation of how it could possibly vibrate corresponds to an absorption. So my point here is that there actually is there's not always a direct correlation with the number of signals you're seeing to how many bonds to H there are, for example. So we're going to see that there's an aldehyde stretch here. You actually get two signals from that one H atom, and it has to do with how it's stretching, not necessarily how many there are. So try to avoid correlating the number of signals for a given type of compound for how many bonds to H there are. I see students do that all the time. In order for this absorption to occur, the bond must be polar covalent. So things that have true covalent bonds, so those are basically I mentioned it right here, those are your diatomic elements. Those are completely invisible to IR. And then things that are ionic bonds are also invisible to IR. The way that we utilize this is we actually have chambers that are made out of salt. So we went the cheapo route and used sodium chloride. And honestly, I have seen silver chloride plates, and they basically cost triple the price for about the same level of accuracy that we need in this class. So some labs do have the fancy AgCl plates, but we are going to go ahead and use sodium chloride plates. So when we get to lab this week, I know some of you guys have labs tonight, and some of you have it on Thursday. When you're done with your salt plate, you should throw it in the sink and wash it in the soap and water? No. Sodium salts are soluble. So it's basically all these plates are. They are rock salt that have been machined to be nice and smooth. And if you get pure rock salt, they actually are transparent. When you start getting them wet, they actually become opaque. and you can't see through them. So please do not wash the salt plates with water. We use things like organic solvents. That's the whole polarity thing, right? So the organic solvents are used for cleaning these, not water. All right. Another thing also I want to mention here about what's visible, what's invisible, is things that are symmetric and overall appear to be nonpolar. If they're not a true nonpolar covalent bond, they're also still visible in the IR. So for example, the structure for CO2 it's symmetrical in shape. So let me just draw it right here real quick. So this compound, if you were to assign the polarity of it, you're going to see, okay, it's overall nonpolar, and it's all due to the symmetry of the molecule. The thing is, though, that you can have symmetric stretching and asymmetric stretching happening here because of these polar covalent bonds. CO2 is visible in the IR, and it's actually a huge headache to get rid of the signals when you look at real data. So when you guys are doing your homework problems, you're not going to see a CO2 peak, but when you get real data in the lab, getting rid of that CO2 peak is actually part of the process. And sometimes you just can't help it. You have it there. You just got to know to ignore it. But the bad part about it, it actually shows up where triple bonds do. So you have to be able to recognize a CO2 peak versus a true triple bond peak. And they do look different. And we'll see all that stuff today and in lab this week. All right. So these equations here are just essentially summarizing why we talk about it in terms of the units here. So the units here are 1 over centimeter, or inverse centimeters, people like to say. And I will tend to use the word wave number. And it's another terminology here. And it is a function of wavelength, or 1 over wavelength. And you guys remember H and C, those are both constants then, right? So the only thing changing here is 1 over a wavelength, so it makes sense to report these values as a 1 over a wavelength, or inverse centimeter. I have seen, there actually are modes on the instrument. You can actually toggle it to show in wavelengths and nanometers, that kind of stuff, like other units that you're familiar with. All right, next thing here is we have this portion here. That is the spring equation. So if you ever take, I remember I learned that in my physics class. Basically, you're looking at spring strength and kind of energy associated with them. That's exactly what's happening here. And it works out that the spring model gives really good predictions on where the wave numbers show up at for different types of bonds. So what's involved here is this whole thing in front, this 1 over 2 pi c, is a constant. And if you guys go further on in chemistry, especially like physical chemistry, this 1 over 2 pi c shows up a lot in that class. And next thing here is this value for K. That is your spring constant. That's what type of bond you have. And then we have mu, which is the reduced mass, which is a function of what actual atoms are there. All right, so these are the 3 different types of analysis we get using spectroscopy, using a light source. So it's not showing up. This is better in color in the actual website. But basically, if the sample is absorbed into it, we call it absorption. And then what's passing through is transmittance. And then reflectance is the case where it bounces back, and you actually measure it at a different angle. So like typically, if it has reflectance, you're going to measure it at a 90-degree angle from your sample. Where this one's going to be a straight line, a straight shot from your light source. All right, so if you guys have been studying at all, is IR data presented as absorption or transmittance? What's that? It's shown as transmittance. So the way that we look at IR data is signals coming downward is a signal. So they might be these graphs might appear to be upside down from what you're used to seeing from like general chemistry. So looking at this chart right here, a signal are the minimums here. So that's a signal coming down here. That's a signal. So I don't want you guys to think, oh, this part coming up is a signal. That's basically the baseline is up here. All right. There is a relationship between them. I purposely set the IR on this campus to show in absorption. So I want you guys to, every single lab, you're going to have to toggle transmittance. Just because I want you to understand there is a really close relationship between them. So what will happen is, oh look, we have transmittance, and then we want to go to absorb. It basically just flips it. So it'll like the mirror image the graph. All right. So the main reason why I'm talking about that equation, just recapping from Thursday, is that it tells us what kinds of bonds will show up in what regions in infrared. So it turns out that things that are bonded to something heavy and something light, so your OH, NH, CH, they show up in that region. That's your single bond region. And we're going to go over the fine details of the different regions today. I think I'm talking too much. We're going to run out of time. Next portion here is the triple bonds and double bonds. And honestly, this is the useful information. The single bond has a ton of overlap. And what do we call this region? The fingerprint region. So that's that, or the zone of desperation is what I also like to call it. You go there if you're desperate. Something else I want to point out on this chart. So I included this on here. So basically, if you have benzene compounds with different types of substitution patterns, like where groups are attached, you can see these regions. But notice the numbers here. That's well into the fingerprint, isn't it? All these guys are well into the fingerprint. And honestly, I'm going to go ahead and say it on film here. Only worry about that if you're having Professor Hammad for OChem 2, because I don't use this stuff. If I want people to be able to pick out what kind of pattern, I will focus on NMR data to be able to figure out which one of these you have. These are very hard to pick out in IR. But if you have Hammad, he likes to do this stuff. So just giving you a heads up. So I would like for you guys to be able to be comfortable with the top part, though. I do all the top stuff here. Also, I want to point out with this graph is they are literally the same thing, just presented different ways. So just pick whichever one you are comfortable with. I highly recommend remembering this and then getting at these ones via practice. But okay, let's go ahead and enough of me talking about this stuff. I want to start doing it. So let's go ahead and take a look at. I asked you guys to bring this activity today, and this is effectively the lecture for introducing the class to IR. So basically what I do in this worksheet, if you haven't gone through it yet, is I start with like a simple alkane and just kind of go through all the functional groups one at a time. And we're going to see how they show up in IR. So the kinds of things we're going to be building up to here is a very common problem type is if you're given the molecular formula and an IR, piece together a structure. And we did go over IHD, all that stuff with IHD, all that kind of plays into everything here. Okay, so I had a ruler. So I recommend getting a little ruler, like a small one that fits in your backpack to use here. And I like to draw two lines when I do IR, depending on how complicated the graph is. And the first line I like to draw is at the 3000 line. And I'm going to go ahead and draw the 3000 line on hexane and hexene, and then we're going to see how they're different from each other. So there's 3000. Let's just go straight up. That. And then on the hexene, it's the same thing again. Let's just get both these lines in here. Like that. While you're first starting out, you can just go just for practice, but as you start getting better at these more practice, I want you just to visually do this line. You won't have to draw it every time. Okay, so the cool thing about this line is if your compound has a CH, you're going to get a peak near that line. And which side of the line it's on tells you the hybridization of it. So if it's on the right side of the line, the carbon that it's attached to is sp3 hybridized. So we like to call those our alkane CHs. So let's go ahead and write that in here. So this signal right here is for a carbon that is sp3 hybridized and is bonded to an H. So that's like how I like to show it is CsP3H. So that is your alkane CH. And this stuff here, These are things like you're in and out of the plane bending. That's kind of approaching the fingerprint region. I don't care what it is. Because hexane, as you guys probably know, is a straight chain. The only thing in there that we can really see in the IR reliably is the CH. Any carbon-carbons are going to be showing up in the fingerprint over here. So I don't even care what that is. This is the part I'm looking at. So just so you guys are clear, I'm never going to ask you to identify a peak that's in the fingerprint. Unless for some reason you have to use it. But for most cases, no. All right, so what's the difference here on the next one? So notice here how we're starting to get a peak on the other side of that line. So if we draw the compound out, so 1, 2, 3, 4, 5, 6, that means the carbon 1 has an alkene attached. So if it's just to the left of that line, that is your sp2H. So those are the H's that are part of the alkene. So CsP2H on this side. Once again, those are your alkene CHs. And then on this side are your sp3Hs. And those are your alkane ones. And then there is one other peak of significance that we can probably pick out. And it is the double bonds. Double bonds are useful information in IR. They're typically pretty easy to pick out. They show up. You guys remember what shows up at about 1700? I think it was on the quiz for pre-lab, right? What is 1700? That's your carbonyl stretch. And it turns out that a little bit to the right of that, about 1600, is roughly where so 19, 18, 17, 16. So this stuff right here is probably our CC bond. If you're unsure, we can, I think it might be the other one actually, I didn't think about it. But we can double check here if you're unsure, but this is the double bond region. So CC, not seeing it here. There it is, olefin, that's the old-fashioned name for, and that's in the 1600s. So 1680, 1640, roughly in the 1600s range. So once again, this is 19, 18, 17, 16. So oops, that's actually a mistake. I believe it's this one, not this one. This one is actually too low. So a little correction there. So that is a C double bond C. So if we have the C, if you have this here, and you think, okay, that looks like it might be a sp2H, CsP2H stretch from an alkene, you can confirm the alkene by looking for the C double bond C. It has to have both, or does it? So if you have this one, you typically have this one. I do want to point out, though, that if you have this one, you do not have to have this one. And the exception to that would be if you had an alkene that had 4 carbons coming off. So let me just do that example down here. That compound, that would not exhibit a CsP2H stretch because it doesn't actually have a CsP2H in it. So that doesn't work. But we would have the double bond. All right, is it making sense how we're going to use this line at 3000? So just to the right of that is our alkane CHs. So pretty much, or most spectra are going to have that stretch in there somewhere. And then if it has an alkene, we typically have just to the left of that line is the CsP2H. All right. Take a look at the next one. And I want to go ahead and draw that line again. So it's at 3000. Okay. So it looks to me like a bunch of this compound is keeping stuff to the right, but we have this way over here, we have another signal. So just this is going to draw the structure first. We didn't go over naming yet, but 1, 2, 3, 4, 5, 6. That. And I just want to emphasize the fact that this is at the end of a chain, so there is an H attached there. Okay, so this right here, as we see in the previous examples, are all the alkane hydrogens, the CHs. Notice how there are no of the peaks just to the left of that. That means there's no alkenes in this compound. I'm also seeing that there are no alkene stretches at about 1600. That's all empty there, so no double bond. So now we need to find evidence of the triple bond. So this right here is for a CSPH. And that's from an alkyne, but I want to be specific here. This is a terminal alkyne. So terminal alkyne. And all that means is that it's at the end of a chain. If it's on the inside of the chain, or inside of the chain here, that CH is not even in the compound. You don't have a CH unless it's at the end of the chain. And then if you guys have been doing your studying, what is that guy right there? That is our triple bond. Okay. So and this is just like the previous example. So if this is inside of the chain, you wouldn't have this. But if it's at the end of the chain, you have the CSPH as well. And it shows up further left than the CSP2Hs do. So like at 3300 or so is where that one shows up at. The downside of this peak is that certain types of OH peaks show up in the exact same spots. But there's ways to differentiate between whether you have an OH there or if it's from a triple bond. We'll see that in later examples. There is a way to distinguish between them. But you have to be cognizant of that as you're working, that could be an OH, that could be a CH. Do you guys have any questions about anything? How much time? We have 15 minutes. We're not going to finish the packet today, so I'm not going to rush it. All right, same thing for the next guy right here. So 3000, just to be clear what's going on. And this is ethanol. So I want to go ahead and draw the structure here so you know what it is. So it's ethyl with an OH. If to the left of 3000, if you see a broad parabola-like shape, that is your OH. That is the OH bond. And the reason why I show the broad is due to hydrogen bonding. So the thing is, like I'm not sure if you've ever seen like an animation of hydrogen bonding. You basically have bonds forming between all the different oxygens and H's, and kind of ends up being a big mess. And that's all the intermolecular forces we have to push through in boiling things, right? So it turns out we can actually see that in the infrared. So the more OH bonds are in the compound, the more pronounced that OH is, the broader it gets. And we're going to see in the lab that suppose you ran a sample and you didn't dry it first, what you're going to see is this. That whole thing is going to blot out everything. And you might see that just a little teeny little pieces coming out the bottom here. So that is a wet sample. If you see it blotting out the whole thing like that. If the whole baseline comes down, that means you have too much sample on your sample chamber. So if it still has a parabola shape, it means your sample's wet. If the whole baseline is coming down, that means that you have too much sample on the plate. Do you guys see any other signals of significance in here? I think there's like one more that's of note. The alkane CH, right? So we have our CSP3H. That was our alkanes. All right. Out of all the different signals we're going to talk about in this section here, this one should be one of the most pronounced ones. The main ones that I think you guys should know, like without even thinking about it, is the OH and the C double bond O. They're extremely useful. The OH is always the parabola. Oop, here is a good one. Phenol. Okay, just keeping with the same kind of discussion here, I want to go ahead and draw the line of 3000. And I am already noticing that everything is going to be to the left of this line. What does that tell me? I mean about the CHs. What does that tell me about the CHs?
Double bond. SP.
Yeah, so do we have any alkane CHs here? No, there's no alkane CHs. So I just want to point that out. There's no CsP3H, meaning there's no alkane. So every carbon in there that has an H on it is going to be involved, has to be involved in the double bond. And the reason why I'm saying that is because we don't have a triple bond either. All right, this is the OH, this broad peak here. I do want to point out that this signal here was that one I was mentioning that looks similar to the C double bond or the CsPH stretch, and that is a free OH stretch. So just to point things out here, this one is the free OH, and this one is the H bonded OH. So it turns out that if your compound has a lot of carbons in it, like a lot of carbons per OH, you sometimes will have the free OH peak. So once again here, this only happens with a lot of C's per OH. So here we have 6 carbons per OH. This is phenol. We have talked about this compound today a little bit. Okay. We are not quite done with this example. We do have ways to see aromatic rings. And I just want to mention here that this method for viewing aromatic rings is not 100% reliable. So one thing that is reliable is we can pick out the double bond C. So we have 19, 18, 17, 16. So this right here. So that is our CC. Another thing is just to the left of where the double bonds would be, if you see like these 4 fingers coming down. So this portion. And typically, if you have that, you will also have over here at about below 1,000. You also have really deep stretches there too. Both of these together are an aromatic ring, and these are the aromatic overtones. So aromatic overtones, and these are not 100% reliable. And the reason why they are not 100% reliable is because I don't have the spectra offhand here, but I do remember the compound. If you were to capture the IR for this compound, because it has all of the double bonds in conjugation like a benzene does, you actually have aromatic overtones in that compound. So it's not 100% reliable, but it's likely. The reason why I think it's mostly unreliable is because of the fact that sometimes they're not even there. So if they're not there, that does not automatically rule out aromatic. So you will have the double bond though. The C double bond C is guaranteed to be there, but the aromatic overtones are not. They might be there. And hopefully they are when they are. All right. Let's go ahead and do a few more here. So I'm going to show you now the second line I like to draw. So I like to draw a line at 3,000. The other line I like to draw is at 1,700. So 3,000. There's that. So I am already seeing a couple things here. So are there any, we'll come back to that here. So 19, 18, 17, so right here. Then we have that stretch that was on the quiz. And just so we're clear about what compounds we're talking about here, it is benzaldehyde, commonly referred to as bitter almond. Has a benzene and an aldehyde group. No alkanes. So we're not seeing any alkane. Notice how there's kind of a gap there. Did you guys by chance catch what this one is? This double peak? that is your aldehyde CH. So that is a special type of CH. This is your CHO, or more specifically, we're looking at that. And that is a CH stretch. So aldehyde CH. They typically show up as a double peak, and they are kind of buried with the alkane CHs. So unfortunately, sometimes we can't see them because if you happen to have CHs in there that are overlapping that, you can't see them. The thing is, though, that they do have roughly the same intensity when they appear. So it can be a tell for an aldehyde. So suppose I thought I may have an aldehyde by observing the double peak here. I just want to make sure you guys are clear on that. This is the double peak. What else must you have if that is actually an aldehyde? What other kind of stretch must the compound have? CH stretch or something like that? Well, this is a CH stretch here. But if we actually have this functional group, what other stretch does it have to have? Yeah, the double bond. The double bond O has to be in there. And that's what this is right here. This is our C double bond O right here. The reason why I like drawing the line at 3000, or sorry, at 1700, is because if you have a signal that is the most intense in the spectra at 1700, that is a carbonyl stretch. It's typically the most intense peak in the spectrum, most of the time. I don't want to say all the time, because I'm sure I can find an example without not being the biggest one there, but it usually is. What do you guys think this stuff is right there? What's that? That's your CC double bonds. And then that also goes along with this one over here. Those are the CSP2H. And then I am seeing one other little thing of interest, and that is this and this. These go together. And what were those called again? Yeah, those are your aromatic overtones. So I'm just going to write aromatic for now. All right. If you do look at the chart, you can actually do some other analysis where which side of 3000 or which side of 1700 you're on to see which kind of functional group you have. Right here. The main one that I really look at, though, is the anhydride. Is sometimes hard to pick out. That is a double peak. But you can remember these distinct ranges to look at exactly whether you have an aldehyde, ketone, ester. There's usually other ways to pick that out, though. So I don't typically use these values here because there are other ways. But this information is here. They do show up as specific regions. One last little thing I want to show you guys before I let you go for the day. I think I'm going to jump ahead here a little. Yep. So acetic acid. I wanted to jump ahead to acetic acid, and then we'll pick up here next time. But that's this one. So here, I'm going to go ahead and draw the line at 3000 again. And then I'm going to draw the line at 1700, 18, 19, 17. Right? And if you guys remember here, acetic acid has this structure. All right. So then this portion right here is our alkane CHs. So CSP3H. This portion here is the aldehyde. And this one right here is an OH, but I want to be specific here. This is the carboxylic acid OH. So it is a COOH-OH. If you compare this to the alcohol earlier, this is actually really broad. So the one from the alcohol kept itself contained to the left of 3000. If it's kind of wiping out across to the right of 3000, that is a carboxylic acid OH. Another tell that it's a carboxylic acid OH is the carbonyl broadens also a lot of the time. So basically your OH stretch is broadening and your carbonyl is broadening. And the main reason why you're getting additional broadening here is because it can have more hydrogen bonding than a regular OH does. We're going to see it next semester, but the two oxygens that are involved in the carboxylic acid They're constantly playing hot potato with that H. They're constantly just, hey, you can have it now. Oh, you can have it now. They constantly bounce back and forth. And because of the fact that it's not stationary, the OH broadens in the spectra. It's having more hydrogen bonding possible. Whew. All right, so we are at roughly the halfway point. I did want to finish this up today. You could practice, but the rest of this worksheet is the basic stuff, like how to identify functional groups. The real problems actually start in activity 1.3. So if you guys want to start doing practice problems, I recommend going to activity 1.3 instead. And just leave this activity for lecture, because I'm going to finish my lecture with this on Thursday. No, you don't agree with that? You just want to do what you want. Do what you want. I'm just giving you some recommendations. All right, guys, I will see you Thursday. Have the iron structure for acetophenone. So there were the two things that I showed you guys to help you out. One is to draw the 3000 line. And you don't have to do this. This is just to make it visually more apparent for certain things. And then the second one was about 1700. So we have, 19, 18, 17 is right here. Remember that the carbonyl stretch is typically the most intense in the spectra if it's there. And that one's actually touching the bottom. So the one that's right at 17, that is C double bond O. So C double bond O. And then going over here, looking at the CHs, I'm going to just jump over here for a second. We do have some alkane CHs. I'm going to draw the structure here. When I was referencing the compound we did resonance for the first day I recovered resonance class, I was actually referring to this compound. We did the resonance for that problem. It should be in your notes. Okay, so that has some alkane CHs, but it has predominantly alkene or benzene CHs. So these are CsP2H. That little bit right there is CsP3H. So if I didn't know this, what this compound is, to say I just had the data and I had just the formula, I can go, okay, I see that we have a carbonyl, but I'm not quite sure which exact functional group is it. So it's not an amide. We'll see an amide in a later example. It's not an amide, and I'm not sure if it's a ketone or aldehyde by just looking at the carbonyl. So in order for this to be an aldehyde, you'd have to have the double peak also. We don't have that. They're typically pretty pronounced, the double peak. So that tells me that this is probably a ketone, which is what we have. That's a ketone. All right, and if you have a peak that's about 100 away, so 1600 or so, that peak there, you know what that is? Yep, that's carbon-carbon. And there's a few other things we can pick out. I'm seeing overtones for the aromatic ring. So we have this and this. So that means aromatic. And you could probably pick out your CO stretch. And it's like somewhere in this area, but we don't need it, honestly. There are the only time I really think it's useful to start looking for a CO stretch is if you're not sure if you have a ketone or an ester, and that's the only time that I start digging looking for the C single bond O stretch, because it's typically not relevant. I mean, it's not even in this compound. But if this were an ester, you would have a stretch here at about 1100, and if you had the formula for this, you would see that, okay, it only has one oxygen. You don't need to even bother digging for an ester because it has to have at least two oxygens, right? So, for example, if I had an example here where I had two oxygens where it could have been an ester, then I go digging for that. Otherwise, don't. You're wasting your time. And similarly, for the acetic acid, we did this example last time. I would argue that one of this one right here is probably our C single bond O stretch from the carboxylic acid. We don't need that because we already know just by looking at the other stuff that is a carboxylic acid. So Yes, those peaks technically exist, but we don't need it. So only do what you need. And that's the reason why I keep calling the fingerprint region the zone of desperation. You only want to go there if you have to. Just try to avoid it if you don't need to go in there. All right. I'm going to give you the structure here for benzonitrile. You guys could probably figure it out from the name. So we got a benzene, and we probably have a nitrile group. And just include the lone pair for fun. All right. So this particular example could be a little bit tricky. I guess you could draw the line at 3,000. Let's just go ahead and do that anyway, because I think it is relevant here. I just want to see how close that peak is to the 3,000. Okay, so do you think, did that look like a CSP2H or a CSPH? SP2. If it's SP, then it's further out. It's about 3,300. If it's like just straddling that line just to the left, that is a CSP2H. And that makes sense because we shouldn't have that. The reason why I'm pointing that out, if you want to consider if it's a CSPH or not, because we have a triple bond here. So if you see the triple bond, I usually start digging for the CH that would go along with it. In this case, we shouldn't have that because we don't have an alkyne, we have a nitrile. There is no CSPH in this compound. So this right here, that is your C triple bond N. And we also have, what else here? We have the overtones. So the aromatic overtones are that and this together. So that's aromatic. And I am seeing probably one more peak of interest. Yep. And that's this little guy right here. So it doesn't always come all the way down. It's the carbonyl stretch that is usually the one that comes all the way down. The double bonds for carbon are a little bit more variable. Sometimes they're short, sometimes they're long. So once again, we're talking about this one. That is C double bond C. It's at about 1,600. Okay. Next compound, aniline. And I'll give you the structure. This is a benzene ring that has an NH2. And we're going to be using this compound a little bit later, and it kind of smells like a fish died in the bottle when you guys open it. So, yeah, it turns out that a lot of that stinky fish odor in general in nature are typically from amines. Okay, so let's just go ahead and do our 3,000 line again. (19, 18, 17). So like when I first saw this here, I was like, oh, is that a C double bond O? And then you want to check if it is. Like that is the most intense peak in the spectra. If you just go by your gut, you might think, okay, that is a C double bond O. It's not though, because look at my compound. I don't even have a C double bond O. And if you actually count it out, that's at 1,600, not 1,700. That is a C double bond C. Yep. We have overtones again in this one, here and here. Remember, they come as a pair. So that's your aromatic from your benzene. And then we have all of our CSP2Hs. Remember, on this side of the double bond, on the left side of the double bond. And then right here, what is that? That is our amine, and that is specifically an NH2. So that is a primary amine. Wait, let me write it down here. So that is a primary amine / amide. We don't quite know if it's an amine or amide just based on that peak alone, because amides show up there also. So it's just basically your NH stretch. Let me go ahead and erase this. If you have a double peak in that portion, that is for a primary. If you have a single peak, what do you guys think? That's a secondary one because that means 2 of the bonds are to carbon, and then you only have the one H. This is the whole thing where you have the asymmetric stretch and a symmetric stretch. You only have just a stretch if it's just a single NH. If you have two NH bonds, you can have asymmetric versus symmetric stretches. That's when you get the both on there. So actually the next example here, just moving along here, is a primary amide. So there we also see the double peak here. So that is a primary amide. And it's going along with that because over here we have a C double bond O. Let's do the structure real quick. Acetate amide is that. And then what are those? Here? Yep, sp3. So yeah, if they're in the CH region, to the right of the 3000. So CsP3H. And we could probably look up where the C single bond end shows up at, but I'm not going to bother because we don't need it. We have enough information to piece together a structure. So I'm not going to identify every last little peak in there. And you could if you wanted to, but some of it you don't need to. Another thing I want to point out too is notice the different shapes of the peaks here. So one of them, like it doesn't go up back as far as this one does. That is not a characteristic of anything. Like sometimes amides look like this, sometimes they look like that, sometimes amines look like this, sometimes they look like that. But the thing that is consistent is the double peak. So my point is that you can't just use the NH region to tell if it's an amine or an amide. You have to further go on, and does it have a carbonyl or not? So if you have a carbonyl in there, it is probably your amide. Not guaranteed, but likely. So there we go. This one here is a little bit different. I know you guys probably learned a little bit of naming schemes for organic compounds. This one actually has a different way to name. It turns out that if groups are attached to nitrogen, you use that nitrogen as if it were a letter, or sorry, were a number. So like having the capital N methyl, that's like saying, you know, carbon 2, for example. I know we didn't go over naming yet, but I'm pretty sure you guys probably did a little bit in 122, right? So let's use that as a number. Anyway, we only have one NH bond, so we only see that here. So this is a secondary amine or amide. And then we go ahead and, okay, if we think it's an amide, it must have the C double bond O as well to go with it. That's that guy right there. So C double bond O. And then what are these? Yep, that's your alkane sp3H. And I believe that is the end of that packet. We now have all the highlights. So now I want you guys to commit this all to memory before. I am still debating if I'm going to give an IR correlation chart to you guys or not. I haven't decided yet. We'll decide on Tuesday if it's going to be a correlation chart or not. Yeah, if the struggle is real, then I'll probably allow one. Now everybody's like, do poorly, do poorly. So you have to put one on there. All right, so I do want to